Welcome back to our discussion on states of matter. We are into our 7th class on this material. Some of the things that we have discussed in the past include intermolecular forces, and then we introduced the kinetic molecular model, some of its important assumptions, and we were looking at the properties of gases in the last discussion, where we had introduced the ideal gas equation of state, P V equals N R T. This is the ideal gas equation of state. So, if you know any two parameters P, V or T, then you could calculate in principle the third quantity. So, this is the ideal gas equation of state, and we also introduced the Dalton's law of partial pressures. We finished up our discussion in last class looking at some numerical examples on the applications of the ideal gas law. We will continue that discussion now. So, the last discussion centered about, so the numerical examples, the one that we discussed, just to recapitulate, is about a football which is inflated as per the rules of the game. And we used the ideal gas equation to determine the number of moles of air in a football as might be used in a particular game. Okay, this was the first example that we looked at, and we will now continue this discussion a little bit before we introduce the real gases. So, the second example that we look at is about an aerosol spray spray can with a volume of 350 ml, which contains 3.5 grams, 3.2 grams of propane gas as propellant. And we are asked to find what is the pressure in atmospheres of gas in the can at 20 degrees Celsius. So, that is the question. To set up the story, you might have seen these spray cans, that is things like deodorant, and there are other things which use a spray can. What it is done is it has a pressurized gas, and when you apply this propellant gas carries with it whatever that you have. For example, this deodorant molecules etcetera is carried by this propellant gas into the atmosphere or wherever it is applied. And so, we are asking the question, what is the pressure in the can if a can contains 3.2 grams of propane gas and its volume is 350 ml. So, the approach that we take is to use the ideal gas equation. So, we say P V equals N R T, right. So, we have been given the volume, we know that the temperature is 20 degrees Celsius, we know what N is, and we already know that this is the universal gas constant. And so, the thing for us to do is to compute the value of the pressure. So, this is the unknown. It is a very straightforward application of the ideal gas equation of state. So, let us just look at how to do this. There are some practical matters which are important. So, we know, so what do we know? The volume is 350 ml, which in liters is 0.350 liters. This is useful because we will determine the pressure in atmospheres and we will use R in appropriate units. The temperature we are told is 20 degrees Celsius, which is 273, I approximate 273.15 Celsius for 0. So, plus 20 degrees Kelvin, that is 293 Kelvin. Now, we need to determine N. N is the number of moles, which is the mass divided by the molecular weight, molecular mass. So, the molecule that we are looking at is propane, which is CH3, CH2, CH3, that has a molecular mass, molar mass of 15 plus 15 is 30, 44 grams per mole. So, N works out to be 3.2 grams divided by 44 grams mole to the minus 1. So, that is whatever it is in moles. So, now we have N, we have T and we have the volume. All that we need to do now is to plug it in to the ideal gas equation of state, which we write as P is equal to N R T over V, and N is, we have computed, is 3.2 grams over 44 gram per mole times 0.082 liter atmosphere Kelvin to the minus 1 mole to the minus 1, that is R in appropriate units, times 293 Kelvin divided by 0.350 liters. And if you compute this, this goes away with this goes away with this goes away with this, and this goes away with this, that will give you whatever value it is in atmospheres. So, very straightforward application of the ideal gas law. It has ramifications in practical applications, which was what this problem was discussed as. Okay. Let us move on. Let us look at another example where we use the ideal gas equation of state. This is related to density and it goes like this. What is the density in grams per liter of ammonia at 0 degrees Celsius and 1 atm pressure if the gas in a 1 liter bulb weighs 0.672 grams at 25 degrees Celsius and 733.4 millimeters mercury pressure. So, once again we start with the ideal gas equation of state. We say that P V equals N R T. We know that N is the mass divided by the molar mass. So, we say P V is equal to mass over the molar mass times R T, and you bring the volume down to the denominator on the right hand side. We say that P is equal to 1 over m times m over v times R T, and we know that this is mass over volume and that is nothing but the density. So, we rewrite the pressure in terms of the density and the molar mass as P is equal to rho R T over m. So, once you have this expression, this is just the problem that we have is a straightforward application of this expression. So, you are given the pressure. So, we know that the pressure is 1 atmosphere, the temperature is 25 degrees Celsius, which is 298 Kelvin. Oh, there is a small issue here. Okay. The pressure of the volume is given to be for ammonia. So, we say we do it a little bit differently. A 1 liter bulb. So, V equals 1.00 liters. Now, if the volume is 1.000 liters, we say that the mass of ammonia is 0.672 gram, and we know its molecular mass of ammonia is 17 gram per mole. The pressure is given to be 733.4 millimeters of mercury. Now, this problem also illustrates what to do when you encounter pressure in various units. We already said that pressure could be written in one of many units. We have the SI unit of bar, we have atmospheres which we have come across, then we have millimeters of mercury which is the same as torr. So, there are various units. So, what we have is this 733.4 millimeters of mercury. We know that one way of doing it is 760 millimeters of mercury corresponds to 1 atm pressure. So, given that you have 733.4 millimeters of mercury, you can determine what the pressure is in atmospheres, right. You can determine what it is in atmospheres from a straightforward linear relationship between millimeters of mercury and atmospheres. Okay. So, we now have the pressure as something in atmospheres, and we know this expression. So, we have the pressure which is in atmospheres, we know the molar mass is 17 grams per mole, we know this is in liter atmospheres per degree per mole, and this is the temperature. So, once we have this, you can straightforwardly determine what rho is. So, if you wish, you can after that, once you have this at 298 Kelvin, you know the rho at whatever pressure there is, and at 298 Kelvin you can determine the rho at 273 Kelvin and 1 atm pressure. Okay, let us move on. Just couple of more examples which illustrate uses of the ideal gas equation of state. So, we are running to the fourth numerical example. This is an example that illustrates the Dalton's law of partial pressures. When nitrogen dioxide is cooled to room temperature, some of it reacts to form a dimer N2O4 through the reaction to NO2 gas, giving N2O4 gas. Suppose 15.2 grams of NO2 is placed in a 10 liter flask at high temperature and the flask is cooled to 25 degrees Celsius. What partial pressures and mole fractions of NO2 and N2O4 are present? So, let us try and understand this question first before we do the numerical computation. So, let us imagine that we have NO2 at T high. So, in your container we essentially have at a high temperature, which I have called T high, you only have NO2, and when we cool this, so cooled, the temperature becomes T low, and when it reaches a lower temperature, you have in this mixture. So, now in this point the temperature is low T L, and you have both NO2 and N2O4, right. So, this has NO2 plus N2O4, because we are told that at low temperature 2 NO2 gives N2O4. At low temperature. So, to begin with, at high temperature we have only initial, and when we cool the temperature, we have in the same vessel we have both NO2, and because of this reaction we also have N2O4, right. So, we started off with N is 15.2 grams of NO2. Now, there is mass conservation. So, at the end the total number of moles of nitrogen, for example, has to be that which came from 15.2 grams of NO2, and we know the molecular mass of NO2 is 14 plus 32 is 46 grams per mole. So, we know the number of moles of NO2 to begin with, which I call N0, and at time t n final I have n NO2 final plus 2 times n N2O4 final, right, because we have for every molecule of N2O4 we have 2 atoms of nitrogen. So, the number of moles of N2O4 times 2 will give me the number of nitrogen atoms, and the total number of nitrogen atoms that we have is that coming from the NO2 plus N2O4, and that must equal N initial or 0, let us call it, which is equal to N0 NO2, right. So, this gives me one equation relating this quantity that we know with number of moles of NO2 and N2O4 at the end. Now, we need another equation to be able to solve for NO2 and N2O4 number of moles at the final stage. How does one do that? We know that the total pressure is 0.5 atmospheres, and we also know from Dalton's law that P is equal to N NO2 final RT over V plus N N2O4 RT over V, that is P NO2 plus P N2O4, right. So, we have been given the volume, which is 10 liters. We know the temperature is 25 degrees Celsius, is 25 degrees Celsius, which is 298 Kelvin. So, we know these. R, for convenience we will use 0.082 liter atmospheres per Kelvin per mole. So, we know this. So, we get, and the left hand side is known. So, this is 0.5 atmospheres. Keep the significant figures, I have not been very careful about it, is RT over V, RT over V times N NO2 final plus N N2O4 final. We know all of these quantities. So, we get another expression involving the number of moles of nitrogen dioxide and the number of moles of N2O4. So, we have two linear equations, the earlier equation which was just mass conservation, and this from Dalton's law, and you can obtain two expressions for this, which you can then solve to determine the number of moles of NO2 and the number of moles of N2O4. And one final application of the ideal gas equation of state in a practical situation. This is something that we had already mentioned, but we will just go ahead and try and do this. This is the last numerical example before we move on. Automobile airbags are inflated by nitrogen gas generated by the rapid decomposition of sodium azide NaN3, which is a solid, according to this equation. 2 NaN3 solid gives you 2 Na solid plus 3 N2 gas. If an airbag has a volume of 36 liters and is to be fitted filled with nitrogen gas at 1.15 atmospheres and 26 degrees Celsius, how many grams of NaN3 must be decomposed? So, you understand the question, right. So, what is happening in this? If you understand this, then this is a straightforward computation. You have an airbag in which you put sodium azide. So, this is sodium azide solid, right. Because this is a solid, it has relatively high density, and because it has high density for the same mass, small volume. So, it occupies a small volume. Now, imagine that you are driving in a car which has this bag in which there is a small amount of sodium azide, and it undergoes a collision, although we hope that nothing happens to anybody. So, this car is traveling, we undergo a collision, and when this collision happens, this sodium azide undergoes this decomposition. To give you one solid product and a gaseous product. And we are saying, so the volume we know from kinetic theory, the volume that is occupied is the empty space by this that is taken up by the gas molecules. So, we know that the volume of the container, that is the bag, is 36 liters, right, and we want the pressure to be 1.15 atmospheres, and the temperature is 26 degrees Celsius. So, imagine that you are the chemist that the automobile company has contacted, and they give you that these are the parameters. How much of sodium azide will you put is the question. That is very straightforward application. PV equals nRT, very similar to the first question that we had about the football. Another very practical application. We know the pressure, we know the volume, we need to know N, we know this relationship. So, what are we going to do? We are going to find number of moles of nitrogen to satisfy the ideal gas equation of state. So, this we know and this we know. So, from the ideal gas equation of state, we determine the number of moles of nitrogen, and we know that for 2 moles of sodium azide, we get 3 moles of nitrogen. So, once I know, so 2 moles, so once we determine this, so we get NN2, we know that for 2 moles of sodium azide, we get 3 moles of nitrogen, or you work backwards, 3 moles of nitrogen are obtained from 2 moles of sodium azide. So, for n moles of nitrogen, how many moles of sodium azide we need, right. So, we say that 2 moles, 3 moles of nitrogen are obtained from 2 moles of sodium azide. So, n moles of N2 are obtained from how many, right. So, that gives you n sodium azide, and we know that n sodium azide is mass divided by the molar mass of sodium azide. So, we know this from using this equation. This we obtain from the ideal gas equation of state, and we know this because we know the atomic weight of sodium and nitrogen. So, we can determine mass of sodium azide. This is what we were asked to calculate. Okay. So, straightforward application of the ideal gas equation of state in a practical context. So, this is the kind of thing that you could do. That brings us pretty much, we have discussed a number of things here, and we have also shown numerical examples. So, now we will move on to other things related to the properties of gases. If you remember, so the things that we will discuss next has to do with real gases. You remember in our last discussion we computed what is called the molar volume. So, if you look at molar volume, that is the volume occupied by Avogadro number of molecules at 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere pressure, right. I will write up the table just once again. We are looking at different kinds of molecules, and we will write down the volume. So, we have helium, which is 22.415, hydrogen is 22.428, ammonia is 22.077, methane is 22.360, neon is 22.428, acetylene is 22.274, and just the last one, carbon monoxide, has 22.405. If you will notice, these two have 2 electrons, these 3 have 10 electrons, and these two have 14 electrons. You can look at others if you wish, but this is the volume occupied by Avogadro number of molecules for these 7 gases at 0 degrees and 1 atm. There is some consistency and some differences, which is what we are trying to look at. What often, if you looked at this carefully and if you do this under conditions that are close to ideal. So, what we find is that these molar volumes, so the take home message is molar volume close to 22.4 liters for all gases. This is what Avogadro would have told you. Avogadro tells you that under identical conditions you are going to have the same number of molecules. So, the molar volume is close to 22.4 liters, but not equal. So, that it is close tells you something, that it is not equal also tells you something, right. So, this tells you, so if the gases were behaving ideally, that is some of the things that we use in the kinetic molecular model, that all the mass of a gas is due to the molecules, that the molecules occupy no volume, etc., and that there are no attractive forces, they come and collide, etc., then you expect them all gases to behave identically. So, we are saying that they are close, which means that there are some things which go against the kinetic model, but they are close enough. So, whatever that is, the deviation from ideality is relatively small. So, this is pointing to intermolecular forces that exist. This points to intermolecular forces between gas molecules. Which is the reason for this difference that we see in the molar volumes of gases under identical conditions. So, you could then start to wonder, are there conditions under which most gases will show this ideal behavior, and truly you could find such situation. So, if you go to low pressures, so you decrease the pressure and then you find out. So, rather than look at it at 1 atmosphere pressure, if you go down to low pressures, then you will find that the molar volume would actually, for all gases, works out to be 22.415 liters at 0 degrees. But for convenience we will say 22.4 liters. So, as long as the pressure is reduced, is much lower, then gases behave ideally. But at higher pressures, there are attractive forces between molecules. Which we already know from experimental observation, which is that, I should not say experimental observation, from just looking around us. We have liquids that exist. Water, for example, it is present as a liquid at room temperature and ambient pressure. So, there is evidence to suggest that there are intermolecular forces, right. So, now what we are trying to look at is, can we somehow model the real behavior of gases. So, in kinetic molecular model, we say that there is no attractive force between molecules. So, let us just remember the kinetic molecular model. There were two things, right. One is zero volume of gas molecules, and the second thing that we look at is no attractive force, or repulsive force. If the pressure becomes very high, then it becomes repulsive, but no attractive force, no forces of interaction between the molecules that exist in the gas phase. So, these are the two things that are called into question, and the attractive force, mind you, shows up in the kinetic molecular model by saying that molecules undergo motion in linear form until they undergo a collision with another molecule or with the wall. So, those are the two things that are called into question, right. Before we look at how do we modify the ideal gas equation of state, let us try and do an experiment. Let us look at the pressure volume relationship of a particular gas. So, let us do carbon dioxide, for example, because this was the experiment which was done by Thomas Andrews. And this is what Thomas Andrews did. He takes carbon dioxide into a capillary tube and he applies pressure on it. So, you take carbon dioxide in here and you apply pressure on it and you measure the volume for various values of the pressure. So, this is volume here and this is pressure here. Okay. Let us take a temperature which is something like 50 degrees Celsius or so, for carbon dioxide. At 50 degrees Celsius, carbon dioxide under normal conditions exists as a gas. And if you looked at the pressure volume relationship, what do we get? We get something which looks like a, so you are taking carbon dioxide gas, this is put into a thermostat. Thermostat is something which controls the temperature, and we are keeping the temperature equals 50 degrees. So, you take this whole capillary, put it into a fridge, let us call it, or an oven, keep it at 50 degrees, and you start increasing the pressure on top of this, and at for each value of the pressure you measure the volume, right, and you plot as you change the pressure what the volume looks like, and this is at some temperature 50 degrees Celsius, and you do this for varying values of the temperature. You do the same experiment. So, imagine that you did this experiment in your lab, you have at this particular pressure you measure this volume and so on, right. At low pressures the volume is high, and at high pressures the volume is low, and this looks more or less like ideal gas behavior. We know this, right. This is, how do we explain this? This is nothing but Boyle's law, the inverse relationship between the pressure and the volume at constant temperature for the same mass of gas, which we are not changing. So, this looks like Boyle's law, PV relationship is like a rectangular hyperbola. And now, we do this experiment at low temperature. Imagine this is around 20 degrees Celsius, right. You would say that you have some particular pressure, the volume is high, and you keep increasing the pressure. So, we are doing it here. Let us imagine that you come up to some point here at, so this is being done at 20 degrees Celsius. As you increase the pressure, the volume, as you increase the pressure moving up like this, the volume drops, right. Now, at some particular point the volume changes abruptly, and this is the point when carbon dioxide liquefies. So, at a particular pressure the volume drops considerably. The volume drops considerably because now carbon dioxide, which was a gas earlier, has become a liquid, and we know that at liquids typically have occupy much smaller volume than the gas, and it happens instantaneously, right. At the same pressure the volume has gone from this point to this point. After that, for any small change in the volume, you have to raise the pressure considerably. What does that mean? If I have a liquid, for example, liquid water, even for a small change in the volume of liquid, I have to raise the pressure very, very high, which means that it goes something like this, right. For very small change in the volume, once you have the liquid, for very small change in the volume, so this delta V, this pressure is very, very high. This is incompressible because now I have it's become a liquid, whereas here, for example, for a small change in pressure the volume change is very high. So, I have now this graph for two different values of the temperature. If I raise the temperature rather than 20 degrees, you do it at 25 degrees, it looks very similar. There is a point at which carbon dioxide liquefies, this volume drops to here, which corresponds to a liquid, and once it is a liquid and it moves, and you do this at various temperatures and you plot this, and you will find that this looks like a dome, right. And this point, above this particular point, the temperature, so imagine there is a temperature here, above this temperature, and this temperature is somewhere around 30 degrees Celsius, a little above that, 31 or so degrees Celsius. Above this temperature, no matter what you do to carbon dioxide, it will never form a liquid. So, this temperature above which, just by the application of pressure, you cannot liquefy is called the critical temperature. So, this point here is called the critical temperature. Denoted T sub C. Now, what are we saying? So, you take any gas, the picture looks very similar to this. There is a temperature T c, above which when you apply pressure, the volume of the gas will look like this. T c is 30 something degrees for carbon dioxide, it will be something else for water gas, it will be something else for methane, it will be something else for nitrogen, but the behavior above critical temperature of that gas will look very similar to the PV relationship for an ideal gas. Well, if you look at the graph, you won't be able to tell. So, it looks like ideal gas behavior, and below the critical temperature, when you apply pressure, the volume shows this kind of relationship. So, in this part, you are going to have a more or less inverse relationship between the pressure and volume. There is a particular pressure at which the gas would liquefy, the volume changes considerably in a very small, well, almost infinitesimal change in the pressure, after which this will go. So, all gases, no matter what they are, will show very similar kind of behavior. And you will notice that as the temperature reaches, if you coming from below, this region, this change in volume from gas to liquid, this dome, if I connect all these points, this dome, this length will shorten until at the critical point it is 0. Okay. So, no matter what, so for real gases, no matter what it is, the PV behavior looks like this, and this was something that was extensively looked at by Thomas Andrews in the 1860s. Okay. Another way of looking at this is by what is called the compressibility factor. Oh, just mind you. So, what are we saying? We are saying that if the gas behaved ideally, that there were no intermolecular forces, no matter which temperature you took, you would have PV behavior like this. You have seen that, right? If you looked at your book, NCERT book, for example, we have seen the PV behavior. For increasing temperature, the hyperbola will just shift to higher and higher values in this PV graph. It will just be like this, but it will be for this, whereas now for real gases we are saying, and this behavior arises as a result of intermolecular forces. So, this is for the PV behavior. There is another thing that we could look at, which is called the compressibility factor, and this is defined as Z is given by PV over nRT. So, what is Z for an ideal gas? So, for an ideal gas, Z equal to 1 for an ideal gas. And what are we going to do? We are going to see how Z looks like as a function of the pressure, right. What are we saying now? Z equal to 1 for an ideal gas. So, which means that no matter what the pressure is, Z for an ideal gas looks like this. Now, if you did this, if you measured Z for various gases at some particular temperature, you will find essentially 2 or 3 kinds of graphs. If you measured Z at some particular, say, room temperature, you will see curves which look like this. You have helium and hydrogen whose Z value at under ambient conditions looks to be higher than the ideal gas value for all values of the pressure. And then you have another kind where you have Z starting negative and then increasing, right. You have O2 and N2 are two different situations. So, you will find two different kinds of things, Z whose gases whose values of Z are always positive and increasing like this, and there are others which do this kind of behavior. And there might be cases where Z is more or less 1 over some value of pressure and then it changes like that. So, but I will consider this to be a subset of this. So, we have essentially two kinds of graphs and we have to try and explain what this is, which is what we will try and do in the next class, right. So, we are looking at compressibility factor as a variation of pressure, which will then tell us how to look at real gases. This is the experimental evidence and then we will introduce the van der Waals of equation of state in the next class and then wind up our discussion of properties of matter by a quick look at liquids, where we will consider vapor pressure, viscosity and maybe boiling point or things like that, which to round up our discussion on states of matter, which we will do in our next class. Thank you.